Hi, good morning. Hope all of you are fine. Now, what about our last class? Last class we have discussed about Cayley's theorem. Now, what do you mean by a Cayley's theorem? Every group is isomorphic to a group of permutation. Now, let's recall what we have done in our Cayley's theorem. For proving a group G is isomorphic to a group of permutation, first we define a permutation on G. We define a permutation for every x belongs to G. We define a permutation lambda x such that lambda x is a map from G to G such that lambda x of A equal to xa for every A belongs to G. Then we proved lambda x is a permutation. Okay. Then we define phi from G to Sg such that phi of x is equal to lambda x. Then we proved lambda is 1, 1, on 2, also it satisfies homomorphism property. No, lambda is not on 2, lambda is 1, 1 and satisfies homomorphism properties. Therefore, phi is an isomorphism from G to phi of G. Okay. So, in today's class, we are discussing definitions of left regular representation and right regular representation of G. In Cayley's theorem, we have defined a map lambda x from G to G such that lambda x of A equal to xa for every A belongs to G. Okay. Suppose we define a map. I am denoting that map as rho x from G to G such that rho x of A equal to ax for every A belongs to G, multiplying A by x. Okay. Now, as in this case, we can prove rho x is also a permutation. Rho x is also a permutation on G. Okay, and if you define a map psi from G to Sg by rho x is a permutation. Sg is the group of what permutation. Rho x is a permutation means rho x inverse. Rho x inverse is also a permutation. Okay. Now what about rho x inverse? Rho x inverse is a map such that rho G to G such that rho x inverse of A equal to Ax inverse. Okay. Now define psi of x is equal to rho x inverse. Then as in the Cayley's theorem, we proved phi is an isomorphism. Similarly, here we can prove psi is also an isomorphism. This I am left you as an exercise. Okay. So this also is an isomorphism. Therefore, this psi is also an isomorphism from G to Sg. Now, clearly the map psi from G to psi of G is 1, 1 on 2 and it satisfies homomorphism property. Therefore, G is isomorphic to a subgroup of Sg. Thus, here we get two maps phi and psi that defines isomorphism from G to a subgroup of Sg. The map lambda x is called left regular representation of G. Left regular representation of G. And rho x is called right regular . Okay, now we are moving to the definition of left regular representation and right regular representation of the group G. Okay, So let G be a group, then the map phi from G to SG defined by phi of x equal to lambda x for all x belongs to G, where lambda x is this one, lambda x of A equal to xa for every A belongs to G is called left irregular representation of G. Okay. Similarly, the map psi from G to SG defined by psi of x is equal to rho x inverse is called right irregular representation of G, where rho x is a map from G to G defined by rho x of A equal to Ax. Okay. Now what about rho x inverse of A? That's equal to Ax inverse. And this is called right regular representation of G. Now we are going to one problem. Find left irregular representation of Klein foregroup. Okay. Left irregular representation means lambda x and this is a function from G to G and lambda x is a permutation. Clear? Now here we have to find left irregular representation of Klein foregroup. Now what about Klein foregroup? Klein foregroup V is equal to set EABC, okay, and with operation this EABC AA, you complete the table. Okay, what about AA? E, AB, C, AC, B, BA, C, BB, E, okay, BC, A, CA, what is CA? B, what is CB? CB, A, CC, E. Okay. Now what is lambda x? So we have Klein foregroup this one. Now first we have to find for every, we define lambda x for every x belongs to G. Here G is Klein foregroup. So we have to define lambda E, lambda A, lambda B and lambda C. Okay. Now what is lambda A? Sorry, lambda E. Now what is lambda x actually? Lambda x is a map from V to V such that lambda x of A equal to xa for every A belongs to V. Okay. So lambda E of A is equal to EA for every A belongs to V. That is lambda E of A equal to A. This is the identity permutation, okay? So what about lambda E? Okay. Now lambda E is actually EABC. Lambda X is a permutation from G to G. Here our group G is V. Okay. So lambda X is a permutation from V to V. Clear? So lambda E is lambda E of E. This you can write confused with this one. Lambda E of x is equal to EX for every x belongs to V. Okay. Now what about lambda x, E of E? E itself, and this is equal to EX is equal to x. Lambda E of A itself, lambda E of B itself, lambda E of C. Okay. Now what about lambda A? Lambda A x is equal to AX for every x belongs to V. Okay. Now draw table for lambda A. Lambda A is EABC and lambda AX is equal to, but we have this definition. Okay. Lambda AX is equal to AX. So first AE, AEA, E, A B C, A C B. Okay, I'll repeat. Lambda A of E equal to A E, which is equal to A. Lambda A of A equal to A, that's equal to E. Lambda A of B equal to A B, that's equal to A B, that's equal to C. Lambda A of C equal to AC, that's equal to B. Okay, we have to find lambda B and lambda C. Now this is our lambda E and this is lambda A. Okay, now what about lambda B? By definition, lambda B of x is equal to Bx. Okay, for every x belongs to V. And now what about here? What about lambda B of E? BE equal to B. What about lambda B of A? C. Lambda B of B, BBE. Lambda B of C, BCA. Okay, so lambda B is this one. Now what about lambda C? Lambda C is a function from V to V such that lambda C of x is equal to Cx for every x belongs to V. Okay, this implies lambda C is a permutation from E, A, B, C. Okay, now what about lambda C of x? Cx, that is Ce means C. Ca means Cab, Cba, Cce. Okay, this is our lambda C. Thus we get lambda E, lambda A, lambda B. Okay, now this, we look at this table. Lambda E, here this is first row of this table, and here these elements are second row of this element, image of A, and this is image of B. Okay, image lambda B is the table row containing B, and lambda C is row containing C. Okay, now we have to prove this lambda. Thus we get permutations lambda E, lambda A, lambda B and lambda C. Now we have to prove this representation. These are the left irregular representation of G, and these permutations, these are permutations. Okay, now we have to prove these permutations form a group. Now what about the operations in permutation group? Permutation, multiplication. So we have to draw table for this one. So here lambda E, lambda A, lambda B, lambda C, lambda E, lambda A, lambda B, lambda C. Now you have to multiply. Here clearly lambda E is the identity permutation. So this is actually lambda E, lambda A, lambda B, lambda C and lambda A, lambda B, lambda C. Now what about lambda A into lambda A? Lambda A, this one again you multiply by E, A, B, C, A, E, C, B. So E goes to A goes to E. And this is equal to E, A, B, C. E goes to A goes to E. Okay, A goes to E goes to A. B goes to C goes to B, and C goes to B goes to C, and this is lambda E. Lambda E. Now lambda A into lambda B. Lambda A, I am not writing. Lambda A into lambda B is lambda A, lambda B, E, A, B, C, lambda B. E goes to B, B goes to C, A goes to C, C goes to B, B goes to E, E goes to A, C goes to A goes to E. C, B, A, E. C, B, A, E. This is lambda C. Okay, now what about lambda A, lambda C? E, A, B, C, lambda C, this one. E goes to C, C goes to B. Lambda A, lambda C, multiplication. Okay, so E goes to C, C goes to B. A goes to B, B goes to C. And B goes to A goes to E. And C goes to E, E goes to A. B, C, E, A, that is lambda B. Similarly, this is if you look at these numbers, A, E, C, B. A, E, C, B. So what about this one? What about this one? This is clearly lambda C. So lambda C, lambda E, lambda A, and this is lambda B, lambda A, lambda E. You can verify it. Okay. And this is the table for the permutation group lambda E, lambda A, lambda B, and lambda C. Okay. So a left regular representation of G is actually a map phi from G to SG. Okay, and such that phi of x is equal to lambda x. This is the left regular representation of G. So here left regular representation of V means is a map from V to SV such that phi of x is equal to lambda x. Therefore here left regular representation of phi of E equal to lambda E, phi of A equal to lambda A, and phi of B equal to lambda B, and phi of C equal to lambda C. These are the left regular representation of a group G. Okay. Similarly, you can find a right regular representation. Okay. So find a right regular representation of Klein foregroup. That is the that I am giving you as an assignment. Okay. So if you look at lambda x, clearly lambda A, what about lambda E? This is the identity permutation. Lambda A is a permutation E, A, B, C, and these are actually row corresponding to the column A. Okay, and you will get A, E, C, B. Okay, now what about if you find row A? Actually, row A you will get permutation E, A, B, C. If you look at table, you will get A, E, C, B. This is actually column corresponding to A. Okay. So left regular representation means you will get here permutation as a row corresponding to A. Here you will get permutation corresponding to column corresponding to A. Okay. Just remember this. Okay. Today we have discussed the definition of right regular representation and left regular representation of the group G. Okay. Left regular representation means it is a map phi from G to SG defined by phi of x is equal to lambda x, and right regular representation is a map psi from G to SG defined by psi of x equal to rho x inverse. Also we have discussed left regular representation of a Klein foregroup. In the next class we will discuss orbits of a permutation.